So many A-level maths students scored 0 marks in this question in their A-level exam last year. Let's make sure it doesn't happen to you this summer. The examiners said that many candidates seemed really to make no progress with this at all because they couldn't find an angle. Or some of them made a little bit of progress, but it just wasn't enough to score any marks at all. Figure 4 shows the design of a badge. Here's the figure. The shape ABCOA is a semicircle, half of a full circle, with centre here at O, and the diameter is 10 centimetres. That's this length here. Let's show that on the diagram, like so. Let's make a note that that's 10. O to B, that's this arc here, is the arc of a circle with centre at A and radius 5. So we're imagining that we've got a full circle here. I've got my dodgy circle. There's the centre at A, and the radius of that circle is 5. Let's show that on the diagram too. Okay, well if that part's 5, well it must also be that this part is 5. 10 minus 5 gives us 5 there too. The region R, shown shaded, that's this region here, is bounded by this arc and the arc BC and the line OC. Find the exact area of R. That word exact is important. It means no decimals allowed. Give your answer in this form, where A and B are rational numbers. What's a rational number? Well, a rational number is just a fancy way of saying a fraction. So we need a fraction here and a fraction here. So one in front of a root 3, one in front of pi. What formulae do we need to know? Well, it's really important that you note that this formula for the area of a sector, which is what we've got shown here in the diagram in green, only works if the angle here is measured in radians. If the angle is in radians, it's a really nice, simple formula, a half times the radius squared multiplied by the angle at the centre, theta. There's another really useful formula you need to know, and that's for the area of a segment. So a segment is this little portion here. The formula is given here, but remember, this only works if the angle theta is measured in radians. So how can we get started with this question? Well, we're going to draw in 2 lines, which are going to shed light on everything. There's the first line I'm going to draw, and here's the second line I'm going to draw. Why is this so helpful? Well, remember the lengths that we had on our diagram earlier. How does this help us? Well, remember that we had a circle here. A circle centered at A and of radius 5. There's a radius. That's 5. Ah, there's another radius. So this length here is also 5. Let's put it on the diagram. That is 5 centimetres there. But remember, we also had a second circle. We had the much bigger circle here. What can I do with this circle? Well, for this circle, remember the diameter was 10, the radius was also 5. There's a radius there, but also here's a radius here. So that's also 5. So what kind of triangle do we have here? ABO. Well, all of the lengths are the same. They're all 5. So what kind of triangle is this? It's an equilateral triangle. What do you know about the angles in an equilateral triangle? Well, they're all equal. All of the interior angles are all 60 degrees. But remember, if I want to use these formulae that we have, we need the angle to be in radians, not degrees. You should know that pi radians is 180 degrees. So what would 60 degrees be? Well, I'd need to divide by 3. Pi by 3 would give me 60 degrees. That's this angle that we've got in here and at the top as well. I'm not going to bother drawing that one though. Okay? What other angle might I like to find? Well, it might be helpful for us to find this angle in here. How could I work out that angle? Well, I know that this entire angle is half of one full term. It's going to be 180 degrees, pi radians. But I need to take away this part, the pi by 3. Pi take away pi by 3 gives me 2 pi by 3. So that angle there in blue is 2 pi by 3. So how am I going to form this shaded area R that we've got shaded here? Well, the way I'm thinking about this is I'm going to form it via subtraction. I'm going to take this area here of this entire shape. That's a sector, the sector of the big circle that we have, centered at O. And from that, I'm going to subtract this small little area here. That's a segment of a different circle, the circle centered at A. So I'm going to use these two formulae. I'm going to do area of a sector, take away the area of a segment, but I need to remember that I'm using different circles. So I need to be careful about what I'm going to choose for r and for theta for each of those. Now actually, both of the circles have radius 5. So in fact, I don't have to worry about r too much, that's 5, but we do need to worry about theta. What is theta for the area of the sector that we have here? Because that's what I'm starting with. Well, that's this angle 2 pi by 3. So I'm going to use this formula, a half r squared theta 1, with r, the radius being 5, and the angle at the centre being 2 pi by 3. And from that sector, I'm going to take away the area of this segment in here. So I'm using this formula, a half r squared theta minus sine theta, with r being 5, once again, but with theta being this angle here, pi by 3. Remember, the centre of that circle, we're talking about this circle, is at A. So I'm going to use the angle pi by 3 for theta. If I work out what this is by doing the number crunching, it simplifies down to 25 pi by 3. Remember, I need the exact area, no decimals allowed. What about sine of pi by 3? Well, that's root 3 over 2, and this part is 25 over 2. If we expand the brackets, we end up with this and this. And then if we combine these two together, we end up with this. Now we just need to reorder it. We write the thing with the root 3 first, so this term gets written first, and then we write the thing with the pi. Here it is. So this is our value of A, that's our rational number A, our fraction A, and this number here, 25 over 6, is our rational number, our fraction